Yeah, let's see how we do. So with this one, we're now going to start talking about how to be able to find different angles in space. Okay, so one of the first ones that they have us do is if you've got a plane, and they're drawing this plane, and you've got a line that goes through the plane. Okay, so if you think about it, if we could figure out what this vector was and that vector, well, we already know that that is okay, sorry. Hang on just a second. Do you know what? Can you give me 5 minutes?
Yeah.
Okay. Sorry. So if we knew a vector and another vector, right? Like if we're trying to find this theta, and this is vector A and this is vector B, we already know that that's cosine of theta is equal to, what is it, the dot product over the magnitudes? Okay, well that gives us, that's with cosine there. So if we knew this angle, or excuse me, if we knew this vector, then we could use the cosine like we've always done. But the problem is if you think about this plane, there are infinitely many vectors that are sitting, like if this is the plane, like we're sitting, this is the weirdest video, we've got all these different vectors going different directions. So we can't necessarily just come up with one vector. But what we do know, what would be unique?
The angle that's going downward.
Okay, this angle is unique, I agree with you, but this vector, the normal vector, is also unique. There is one particular vector that's normal to the plane.
The top.
Does that make sense? So it's
The cross product.
the cross product. Okay, so if we knew a couple vectors from the plane, we can take the cross product and we can get this normal vector. That, or some multiple of it, will always be, like we've got just one option there. Does that make sense?
Yes.
Okay, so but if we have that angle, or if we've got that vector and then we've got this vector, we know the direction of that line. Well, this is no longer it's no longer cosine, like adjacent over hypotenuse. It's now sine. So what we do here is instead of cosine, let me say that a different way. This angle right here, do you see these theta angles? Those are going to be the ones where you're using this direction vector and this normal vector, but I don't want to find this angle. I want to find that angle. And so if you think back to geometry, if you have A, B, C, and this is little a, little b, and little c, then what happens here is if you have sine of A, that's equal to A over C, well, cosine of B is equal to A over C. Since these things are complementary, the sine of one equals the cosine of the other. Okay, so that's what we can use up here. We don't want this angle between the normal and the line. We want the angle between the plane and the line, and so we have to use sine instead of cosine.
Okay.
Does that make sense?
Yeah.
Yes.
Kind of. Okay, we can jump in and see, we can jump in and see an example of that. But the other thing that's cool, hang on, we're getting inventive here with our videos. So sorry, maybe you've come to class. I don't know, I'm just kidding. The other thing is if they're asking us, they may ask us to find the angle between two planes. Well, so I love this diagram, if you see this one. So here's a plane, here's a plane. The angle between them, hang on, I need to look at the book. If we're trying to find the angle between the two planes, what happens is if we can take these two normal vectors, this ends up being a lovely little quadrilateral. And so, do you see that?
That is.
So this is 90, this is 90. These two right here have to add up to 180. Think back to geometry. And so this one right there, that's 180 minus theta, therefore if this is theta, then that has to be theta. So when we're looking for the angle between two planes, we're just going to use the normal vectors of those two planes.
Okay.
Does that kind of help?
Yeah.
Okay, I'm sorry if this is a terrible video, but it's better than nothing. So there's a couple examples in there, and then we're going to practice all of that. Yay!